Euclid's Elements, Book 1, Prop 24. If two triangles have two sides equal to two sides respectively, but one of the angles contained by the equal sides be greater than the other, then the base will be greater than the base. So here's our givens. We have triangle, try to draw this where it's obviously containing a larger angle. So here's triangle ABC, and this side is equal to this side, and this is triangle DEF. So this side is equal to this side, and this side is equal to this side. So two triangles with the sides equal respectively. But the angle contained between them is unequal. Therefore, this angle is greater than this angle. Then we're going to prove that the base BC, opposite the greater angle, is larger than the base EF. So here are our givens. We're given that AB is equal to DE, that AC is equal to DF, and that the angle at A is greater than the angle at D. From that, we're going to prove that base BC is larger than the base EF. We're going to start this proof. If these angles are unequal, we can make an angle equal to a given angle at a given point. So at point D, let's build an angle equal to the angle at A. And we can do this because of Prop 23, which allows us to make an angle equal to a given angle at a given point. So we're going to make angle DE. Let's see, we'll end up calling this G. We're going to make this angle equal to the angle at A. So angle FD G is equal to the angle at A. And we're going to cut off from DG, we can extend this as long as we want, but we're going to cut off a portion of this longer line so that it's equal to either AB or DE. So we're going to make DG equal to AB or to DE. It's the same. This is Prop 3 allows us to do that. So now this line is going to be equal to this line or this line. And now we're just going to connect points G and lines of the GF and GE, which we can do from Prop 1. Don't connect any 2 points. And now let's look at this triangle, triangle GDF, and compare it to triangle BAC. And we're going to see they have two sides equal to two sides respectively, and the angle contained between them equal. Therefore, the base is going to be equal to the base. So BC is going to equal GF because of Prop 4, side angle side. Now let's look at this triangle. Let's put it in green here. But this triangle DGE. DGE. In this triangle, we have two equal sides. Therefore, we have an isosceles triangle. And therefore, we know that the base angles of an isosceles triangle are equal. So I'm going to color block those. Here's this angle, base angle, and here's this base angle. And we know that those green angles are equal because of Prop 5. Base angles of an isosceles triangle are equal. From this, it's clear that the angle here, GEF, which contains this green angle in purple, this purple angle is obviously greater than the green angle because the whole is greater than the part, which means it's also greater than this other green angle. So it's greater than either of the two green angles. And that's common notion 5. And we can also note, let's see if this will show up, that this angle here in blue is only a part of this angle here in green. Therefore, the green angle would be greater than the blue. And since these two greens are equal, we can say that the green angle is greater than the blue angle. So notice what we have. The purple angle is bigger than the green, which is equal to this. So this purple angle is bigger than this green. This green is bigger than this blue. Therefore, the purple angle must be much, much greater than the blue angle. Again, this is just an application of common notion 1. Oh no, common notion 5, the whole being greater than the part. So we have this angle here, GEF. I'll put it purple. GEF being much, much greater than angle FGE, the little blue angle. But in this triangle here, now let's consider this triangle, we know from Prop 19 that in a triangle, the greater angle is subtended by the greater side. So since this angle in purple is much, much greater than the angle in blue, we know the side subtending this angle, namely this line here, is going to be much, much bigger than the side subtended by this angle, which would be this one here. Therefore, we know that the side subtending this, which is GF, must be greater than the side subtending the blue, which is EF. And GF, remember, was proved to be equal to BC. Therefore, BC is greater than EF. And that's what we're trying to prove, that the base BC is larger than the base EF. Since we have done that, we conclude our proof with QED.